Good afternoon, everybody, and thanks for coming along. I'm here to talk about battery modeling and simulation solutions, chiefly within the Ansys software ecosystem. So we're going to talk about the whole process of battery simulation, and then the sort of latter two-thirds of the presentation will just be focused on the application of LS-DYNA, so Ansys LS-DYNA for ensuring battery safety and performance, and really with a structures side or structures preference, but I will touch on the other technologies as well. And really in essence, what we're going to look at if we're deforming or damaging these batteries, lithium-ion cells, for example, how likely it is that they will then go on to fail, potentially catastrophically. So we're going to look at how this can be achieved through simulation. We're going to look at how some of those simulations might sit within the overall battery design and deployment workflow. And really, electrification and the role of battery simulation. Well, electrification and batteries, batteries are a vital part of our drive to decarbonisation. It's not a new technology. We've got, courtesy of Wikipedia there, we've got Gustav True's tricycle in 1881, one of the first electric vehicles. But then things sort of diverged away from that when the ICE or combustion engine came to the fore. But really, sort of current or recent developments and environmental drivers are ensuring that we really must develop and deploy these technologies. In the context of transport, it's absolutely vital. ICEs are one of the primary burners of fossil fuel and one of the major creators of greenhouse gas. And we do have a responsibility to minimize and eliminate that. But it's not just transport, it's applicable over all energy sectors. So yeah, we're looking at sort of the process of electrification really, and how we can integrate simulation into that whole environment. And it's all well and good generating our electricity in an environmentally responsible manner. We're getting really quite good at that. Solar panels, renewable energies, wind farms, etc. But these are all transient sources of energy, aren't they? We need some means of then storing that energy and enabling that energy to be stored and transported and utilized. And that's got to be done in a means that's safe, it's got to be efficient, and it's got to be cost effective if it's going to be viable for the mass market. And really the only way we're going to achieve that is utilizing simulation to accelerate some of these battery development processes. And that can enable us to reduce cost. And at every stage, we want to eliminate or mitigate risk. I'm a classic structures engineer. I'm averse to risk. And it's been one of my main drivers in my career of minimizing or eliminating risk for users of the technology we're designing. So my objective here is really to show you how some of these Ansys tools can be used to achieve this over the whole of the battery lifetime, right through from conception and design to manufacture and deployment. And then we've got to consider, well, what are some of the challenges in battery development? None of you will have missed the headlines in the news about exploding lithium batteries and the resulting catastrophic fires that we can result from that. And this has cost too many lives, in my opinion, and it's absolutely incumbent on us as engineers to minimize or eliminate that danger. So safety concerns are paramount. This is as a result of thermal runaway when we get short conditions in cells, for example, or through poor charging regimes, or poor integration of these battery cells into overall systems. But we also need to optimize their performance, don't we? We need to make sure that we're maximizing the energy density and the power output whilst minimizing cost and weight, for example. We also need to enable fast charging cycles without negative thermal connotations. Nobody's very happy, are they, if they're sitting at a service station for a couple of hours while a trickle charge goes into their cells, and then when there's a sort of hypercharger next door which is going really rapidly. So we need to make sure that whenever we're thinking about these battery systems, that we've considered how we're going to charge them up and how quickly that can be done without then leading to thermal problems. And we can simulate that. Certainly, we've got to make sure that we've got to ensure the durability of our batteries. They will inevitably degrade under use in real world conditions. But we have the opportunity here to slow that degradation through careful consideration of design and manufacture and some of the right material properties and some of the operating conditions. And we can consider that virtually. We can simulate that before we put it into practice. So we can then ensure we get the maximum lifetime for our batteries. Clearly, that gives you the best return on investment. So customers are happy, consumers are happy, but it also gives us a viable business. We need to ensure that durability. But then there's absolutely no point in designing our sort of perfect battery system if it can't be manufactured cost effectively. And so we've got to then consider how we're going to manufacture these systems. And again, I had to bang on about it, but we can simulate that. So we can actually simulate things like some of the forming operations, some of the manufacturing processes, some of the thermal conditions that are undergone when you're manufacturing these systems. So several stages through the whole design and concept to deployments cycle, we can use simulation. And then finally, and perhaps most fundamentally, we need to demonstrate the safety and the performance of these systems, probably as part of a regulatory and environmental requirements. So if you're working in a safety critical industry, it's more than likely that you have to answer or demonstrate compliance with code. And simulation again enables us to do that. Okay, you may be doing some tests, some backup tests as well, but that test, the combination of test and analysis prediction can give very, very good evidence that you're compliant with your regulations. And it probably in many industries is actually, it's a prerequisite of sending these systems out then to the consumer. But at each of these stages, simulation is an essential tool for assessing that. So we're evaluating and quantifying the performance of these batteries. Now I've taken the liberty here of breaking this process down into sort of 3 key stages. So firstly, we're looking at the sort of cell to pack design stage. And this is where we're really considering the fundamental physics of the operation of the cells. For example, we're looking at the electrochemistry. We're looking at the electrode design, so the state of the charge in the system. We're going to consider things like thermal management and runaway. We need to cool these cells as they're being charged up. We need to cool them efficiently and appropriately. We also need to consider, if we do get these runaway conditions, that they're controlled and that doesn't lead to a catastrophic behavior or catastrophic failure. And sort of complementary to that, we need to consider mechanical abuse. If you drop a cell or if you puncture it, then how is that going to behave? What's going to be the problem for that? And how can we minimize or reduce or eliminate the risk to the structure? And again, we can consider durability, fatigue failure or long-term viability of these systems. And it's not just the cells. We can start looking at durability of the associated circuitry as well. I'll touch on that later. So at this first stage, really what we're doing, we're getting into the weeds of how our cells and our batteries operate. Now the second stage, once we've got those analyses results and our sort of physics set up, then we need to consider how that can be integrated into larger scale systems. And this is where things like the battery management and system integration come to play. So the sort of center top trumps card here it was taken from an Ansys example for the automotive industry, but it's applicable in any industries where we're going to consider cell deployment. So we're able to simulate the integration of these cells and their operation within system level models. So we're looking at we can generate a reduced order model from our original analyses that we've done in stage 1 in the cell and pack design. And we can use these reduced order models then to really almost instantaneously give us feedback and an idea of how our cell is going to behave in the overall system. And then the final stage there, the order might not be entirely right, but the final stage is then once we've got these proposed cell designs and solutions, we do really need to consider how we're going to manufacture it. You can see there, for example, we've got a simulation of a roll forming of a particular component within a cell. And we've got a broad and deep means of doing this. We can use exactly the same simulation technologies we've used in the first stage for doing this simulation of the manufacturing. And it is vital at this stage. We can do the sort of full, as it says there, the full digital engineering solution is what's available to us. And we can do things like accurate electrochemistry. So these are those 3 fundamental stages. But then how might we achieve that? Well, here we are. We've got a slide here of some of the software we can use, but a full text slide is a terribly dull slide. So let's jump over that. And let's look, actually, this is a nice graphic of really the ecosystem of software we might consider and and how it sits within the design process. So we're going from left to right, from conceptual requirements and preliminary design. We're then going to consider the detailed design, so our sort of 1, 2, and 3D models of these systems. So we're considering electrochemistry, aging, structural, thermal. And this can be in a variety of pieces of software. We can do geometry, manipulation, and discovery. We can do structural analysis and Ansys Mechanical and LS-DYNA. We can do our conjugate heat transfer and other fluid in Fluent, so CFD. But it is worth remembering we can also do things like EMI and EMC simulation. So when you've got power circuitry associated with the charging and discharging of these circuits, we can actually look at how they're going to behave, electronically or electrically. So we can do these Maxwell solves, for example, or we can look at the HFSS, the frequency response, in the electronics desktop. So we can pretty much cover all of the physics that we need to cover to represent the behavior, the physical behavior of these cell systems. And then we can step over that once we've got our structural and our thermal and our electromagnetic solves done. We can then integrate that using these systems integration level tools, so the battery management systems, into an overarching system. And there is software available for each of these different stages. And then we can again model battery manufacturing. And ultimately we'll end up with some of these digital twins. So this is sort of utilizes things like a reduced order model that's dragged in or aggregated a lot of our simulation data, and is instantly accessible for systems level and for sort of sustainability and operational simulation. So it really is a very, very rich ecosystem. And one of the beauties of this ecosystem, being Ansys, is that all of these different bits of software talk to each other pretty seamlessly, actually. It's all within one, or it can be integrated in one large overarching system in a very familiar environment. So it means that the generation and the sort of simulation of these systems can be done quite efficiently. So just a bit more detail on some of the individual packages. So again, we sort of move from left to right this term in terms of functionality. So we've got, for our battery and cell pack design, we might take in CAD data, or we might generate some native geometry on which to model out, or on which to generate then our fluid or our structural or electronic model simulations. So we can do that in Discovery. So Discovery is a really nice package for geometry simplification or generation of native geometry. But it's also nowadays it's got it within there. It's got a very efficient GPU-based solver for CFD, for structural, and for electromagnetic. Now, that's not a fully featured solver, but it will give you an initial look-see, a good idea of, say, the linear static structural response, or some of the more fundamental CFD analyses. And it does that in almost real time because it utilizes the GPU. So we can use that to really very quickly do some look-see analyses. But then probably what we're going to want to do is then promote that up and do a more full-featured analysis, say a structural analysis in Ansys Mechanical or in LS-DYNA or a CFD in Fluent. So we can take our geometry and we can take any modeling efforts we've done in Discovery, and we can promote that into these more full-featured packages, really, simulation packages. And you can see that those are appropriate both for the cell and pack design and also for the battery production process. If we're looking at durability, well, we can consider ENCODE design life. That's really good at looking at fatigue and thermal fatigue problems, and it's a very full-featured package for doing that. You can do a certain level of durability within say Ansys Mechanical, for example, but if there's some really advanced features, then we can consider ENCODE. Now, if you're looking at simulating the manufacturing process, well, for example, if you've got granular media moving through a process, a production process, then we can start using something like Rocky, a discrete element method solver. So we can look at simulating some of the manufacturing processes. Again, Fluent, Mechanical, Discovery are all relevant for the manufacturing as well. And then we've got other things. We've got polyflow for injection molding. We've got multiphysics capability. Now, multiphysics is where we're looking at the interaction between the fluid behavior and the electromagnetic behavior and the mechanical behavior, all within a single simulation. And we'll see an example of that for LS-DYNA later on. And then, us analysts, we spend a lot of time generating these lovely, lovely models. But they shouldn't just be a model of a single situation. What we can do, we can use software like OptiSlang to change parameters within our model. So things like thicknesses or weights or materials. And we can start optimizing. So we can optimize against mass, we can optimize against performance, we can even optimize against environmental cost of manufacture. And OptiSlang is a sort of overarching piece of software that will talk to all of these simulation softwares, be that Ansys, be that external, and even taking test data. And it will wrap all of these, and it's a very, very powerful and flexible framework for optimizing the performance of our batteries. But we've got to be honest with ourselves. This isn't light computation. These can be computationally quite expensive simulations to do. So almost invariably, we're going to need some level of high performance compute to do it. You know, these days, all the modern simulation software have got a capability to be deployed to the cloud or to be submitted to a remote cluster and run on huge multi-core environments. And they do scale very well. You know, Fluent CFD scales incredibly well on GPU and CPU. LS-DYNA will scale very well on multiple cores of CPU. DYNA and Ansys Mechanical, again, scales very well on CPU. And in fact, the 2025 release is starting to get in some really powerful GPU scaling capabilities as well. So I would expect that if you're considering this as a sort of simulation you need to do, then you're going to have some HPC. And the remaining three on the right-hand side, they're the sort of simulation or the systems level simulations. But it's worth seeing Granta there. Granta is a materials database that's integrated into this whole environment and enables us to make material choices and bring in traceable and reliable data directly into our simulations without having to go and rifle through published papers or type data in manually. And it's also a means of if you've got enterprise test data, for example, of integrating that and making it accessible to your engineers. So it's a very, very powerful ecosystem for doing this. We can see there I've got the smiley face. LS-DYNA really is my happy place. This is where I spend a lot of my professional life really is doing explicit analyses or DYNA analyses. It's a piece of software I've got quite a bit of experience in. So inevitably in any presentation, man with a hammer chooses the big nail, don't we? So I'm going to focus on LS-DYNA from now on. And I don't really think I can beat Ansys' own summary slide of what LS-DYNA can do. So I'm going to recycle it. This is their marketing slide for battery abuse under crash load cases. So what we're doing here, we're considering the battery behavior under abuse conditions, so dropping, puncture, or even a catastrophic crash event. And what we need to do, we need to make sure that if we deform these structures or heat them up extensively, that they're not going to then give way to this thermal runaway, which can lead to gasification, which can lead to explosion. And LS-DYNA provides us the means to simulate this. It's a multiphysics, so it can account for electrochemistry, structural and thermal, and all at different length and timescales in a single analysis environment. And what it means is it gives us the capability to predict those behaviors and assess their performance and mitigate risk. And it is by far a cheaper means of achieving this than doing repeated and incremental physical testing. I suspect you'll never eliminate physical testing, large-scale testing, but you may only have to do one at the end of a design process and not iterations on the way to that final design. You're always going to need test data for materials, and more than likely you'll need some sort of lower-level coupon or localized model of an analysis methodology in order to validate that before you can deploy it to larger-scale analysis. So I'm not saying that we're eliminating test, but we can minimize it. And we can vastly reduce and reduce the timescales for development. So here we go. The risk of any presenter. We'll put some equations on the screen, but I don't think we need to be intimidated. Really, what I'm showing here is the interaction between the different solvers within LS-DYNA. So you can see, for example, the displacement and the temperature are interchanged between the mechanical and the thermal solves. So at a particular dynamic time step, what happens is the thermal solve will be done. The updated temperatures are then fed back to the mechanical solve, which obviously if you've got CTE in there or thermal expansion, then that can be accounted for. And similarly, we can see that the thermal solve will interact with the electrical and the electrochemical solvers. So we can get a prediction of the joule heating. whenever we heat up a material, its conductivity will naturally and its resistivity will change. And using these coupled analyses, we can account for that within a single environment or analysis environment. There's even the ICFD solver here, and there's actually a CESE solver behind the scenes as well. So we can model cooling and fluids within these systems. I'm not going to cover that today, but you'll have seen playing on the right of the screen, there's a couple of CFD solves. These have been done within LS-DYNA, and they can couple with the electrochemical and with the structural response. So it's a single sort of analysis environment for accounting for all these different behaviors. And there are some computational challenges. If you think of a lithium-ion pouch, you've probably seen them when you're taking your phones apart. They're fairly simple. They're fairly innocuous-looking things, but there's a complex range of multiphysics in there. We've got to take account of all the mechanical properties. We need to account for its electromagnetics. We've got electrochemistry and thermal. So it's evident we've got a wide range of interaction physics here. But that really is music to the ears of someone who's got LS-DYNA available. And we've also got a large range of length scales, haven't we? If you look at the size of a Tesla battery pack, for example, it's of the order of a couple of meters probably. But then we've got individual cell layers within the batteries of sub-millimeter size. So accounting for those different length scales is difficult. Similarly, the timescales involved are widely ranging. A typical analysis for a crash may occur just over milliseconds, but some of these thermal problems may take place over minutes, hours, or even days. So we got a wide range of timescales to consider as well. But it's all doable. And the only reason I've got a Ford Focus in here is actually a lot of the original development work for this was done between LSTC and Ford in close conjunction, and then subsequently LSTC were bought by Ansys. So it's worth acknowledging that Ford were involved very early on in sort of the development of this technology. And then in terms of how they're modeled, well, this is achieved within LS-DYNA through using equivalent circuits. So within each layer of the cell, we've got each of the different layers is discretely represented. So we've got the collectors, the anode, the cathode, and the separator. So we've got a graphical representation of that down in the bottom right of the screen. And then what we can do, we can actually impose Randall circuits, they're called, between the shared nodes or between the nodes on the surfaces. And this is how we can then start simulating our electrical behavior. So I say that, yes, these layers are discretely represented, but luckily for the analysis or the analyst, this is done easily within the model definition. I'll show you a very quick demo of that later. So this is what we do. We impose our Randall circuits between our nodes, and then this enables us to impose some electrical behavior on the system. It's a very mathematically efficient way of doing it, and it was quite easily integrated into LS-DYNA. And one of the real strengths is it then enables us to model things like internal shorts. So you can see on that bottom right, once we've deformed those outer layers sufficiently, so the collector layers, we can penetrate through the middle separator, and then potentially those conductors can contact, can't they? We'll get a thermal short, which will lead to increased temperature, which can ultimately lead to some fairly catastrophic events, but we can simulate that now. So this is just a very, very brief overview of how that's done within LS-DYNA. You've got these sort of RC circuits really that enable us to impose our Randall circuits on the assembly. But I think because this battery modeling capability is such a strength and current market conditions are such that I do think that this is going to have a lot of development in the near future, and there'll be increasing functionality within each of the releases. But that's enough of static slides. Look, here's an example. So this is a steel sphere coming down. It's impacting on the top of a layer of 8 different lithium pouches or lithium cell pouches, which in itself is a structural problem. It's not desperately surprising, is it? We can see that we get some significant deformation. But now we've got the capability to actually see, well, if we've got enough deformation within there, we might get a short condition. And that short can lead to thermal or temperature rise. And this is exactly what we're seeing on that right-hand side. So you can see that as that battery comes down, or as the steel ball comes down and impacts on that battery, it induces that shorting, and we get a thermal rise, a temperature rise. And just a bit more of a sort of glimpse of how this is achieved. So you can see on the right hand side here, within each of our finite elements, so this is what's called a thick shell finite element. It's a very computationally efficient way of modeling that deflection, but it enables us to then put in discrete representation of all of the different layers of each of those cells within that. So within a single finite element, we can have a number of different layers, so the cathode, the anode, the separator, etc., and multiple copies then of those, so we can stack up cells or layers within our model, but maintain the computational efficiency. Look, we've only got, and I've already spoken for half an hour, and you cannot cover this in huge detail. So there's a couple of really useful references there which are worth digging into if you've got the time. So what I'm going to do now is just I'm going to summon the demo, or the demo demons, and we're just going to do a quick look at how we might achieve doing these models. So the first thing I'm going to show you, this is a piece of software called LS Pre-Post. So this is the pre and post processor for LS-DYNA. It's complementary to sort of workbench mechanical, but it's a very closely coupled way of generating an LS-DYNA model. And the chief reason I want to show you this, because it's got a convenience tool in here. So in the applications menu, we've got this battery packaging tool. And what this does, this presents us with a fairly straightforward sort of dialog box that's got 5 different key stages in it. So if we then populate data within each of these 3 stage or 5 stages, this then, what LS Pre-Post will do, it will then go and generate you the FE model with the appropriate materials applied. And it's a really accelerated way of generating some of these cell models. Now, there's nothing more tedious in a demo than watching somebody typing in numbers and maybe swearing a bit because they mistyped a number. So I've taken the liberty of pre-populating this. So you can see here, this is our example. This is our steel sphere impacting those cells. And this is just an example of how you might put in the data. So we can have an origin point. We can then control the width and the size, or the geometric size and configuration of our cells. And within each of those cells, what we then do is start building up layers. So you can see in here, for example, layer 1, this is my collector. I've got a positive electrode. I've got a separator. I've got a negative. So these are the different layers within that. And you can see within each of those, I associate a different material type. So behind the scenes, what I've done, I've input my Poisson's ratio, my modulus, my various electrochemical or electromagnetic properties into the model. And it means that I can then very, very quickly generate these systems of cells. And there's a real convenient way of doing it. I can now copy that multiple times. So I can now generate pretty advanced layups, for want of a better word, of cell configuration. And these are then applied automatically to a model. Similarly, I need to put in things like my Randall cell properties or my state of charge. So you can see in here, I've got a cell capacity Q. I'm giving an initial state of charge. So this is where I'm inputting my parameters that will control the behavior of the model. Again, we've got our various resistors or capacitance inputs for our RC circuits, our Randall circuits. We've got a temperature input. So as soon as we work through these different tabs, so we've got multiple cells here. You can see I could put in, say, I want 8 cells in the Z direction. And then if I press create, what we'll end up is this configuration model for us very quickly. And then all we need to do is to put our boundary conditions on. So we need to restrain this in space. We can add in our details, such as the metal sphere in there, or we can add other assembly details using the standard LS Pre-Post tools, or we can import existing decks, so existing models, and integrate those. So it's a nice, clean, and very closely coupled environment for generating these models. And I think it's very powerful. And then ultimately, we can then do the sort of post-processing of these models in the same software. So we can look at, for example, here we can see this is that model I was showing you earlier. This is the steel sphere dropping and hitting these cells. But don't be misguided. Don't think you're limited just to planar constructions. Now we can consider cylindrical cells. So we can look at the building up these cylindrical cell configurations. And again, we can then impose our structural loads on there or our thermal loads. And we can look how the shorting condition can occur in pretty much any arbitrary different cell configuration. So it's a really, really powerful system of quickly generating these models. I'm very conscious of time, so I might dive back to the presentation, I'm afraid. And it's not just about the external. We can look at we've looked at internal shorting, but we've also got the capability to do some external shorting. So, for example, this is again using that same fundamental model. We've got a steel plate on that left-hand side that we then move through space, and it will actually form contact between the conductors. So you can imagine we'll get a short condition, an external short condition. But again, we can model that, so we can look at the thermal implications of that, and you can see in this case that maybe counterintuitively, the temperature builds from the opposing end of the cell. So this enables us to look in detail at the sort of thermal behavior of this cell. I know these are fairly simplistic examples, but they can then be integrated more easily into sort of full-scale analysis. So you can see here, again, rather shamelessly, these are automotive, but it's clear how this might be applicable generically or generally. So we can look at drop tests, penetration tests, the physics or the associated multiphysics. But I think in these instances, the workflow would more than likely involve a lot of model generation within Ansys Workbench, and then some tweaking and perhaps some post-processing within Ansys Pre-Post. The two are very complementary. And in fact, with each new release of Workbench, more and more of the functionality is being brought into Workbench itself. So it means we can generate these models of very complicated systems in timely fashion. So we said about 45 minutes, so I think 35 minutes is probably long enough for me to talk. What I'd like to think here, I've shown that we've satisfied the goals we wanted to demonstrate. The solution really is seamless. We can integrate all of these physics within a single simulation environment. And that close integration really has fantastic cost and time-saving implications. And if I'm being terribly selfish, it makes my life as an analyst much easier. There's a whole host of different battery models available. I've only scratched the surface. I haven't mentioned meshless methods or some of the fluent capabilities. So be reassured that pretty much all of the physics we need to represent in these simulations is available somewhere, but all within this single environment. I've shown you we can get quite a lot of multi-physics just within that individual LS-DYNA environment. And so I think the benefits of that really speak for themselves. Ultimately, we've got a means here of being more informed about our design decisions and how they might affect structural integrity and safety of batteries. So, and you can see that's a pretty powerful example, isn't it? We've got water flowing here, so a conducting water flowing over external tabs, which is then shorting that. So we've got some structure in here, we've got some electromagnetics, we've got a meshless representation, actually the battery representation in this place, and we've got CFD all coupled together within a single environment. So tremendously powerful way of assessing the performance of our batteries.